Hi, I'm Jared Parsons, a developer on the C# compiler team. In this video, I'm going to be talking to you about the spanf and memory-t types in the system.memory NuGet package. These are new APIs available that we're adding to the .NET Core 2.1 to simplify the management of contiguous memory native buffers while retaining type safety in your code. The first type we're going to dive into is spanf. This is a new type at the core of .NET, which represents a region of writable contiguous memory regardless of how it was created. This means arrays, native buffers, stacked alloc memory, and even raw endpointers can all be represented as a spanf instance. It is the universal receiver of writable contiguous memory. Additionally, spanf is a struct, which means these representations of memory do not cause any heap allocations. Instead, it is efficiently allocated on the stack. Hence, converting from our higher level types like tarray to span does not incur an allocation penalty. Spanf can also be used to view subsets of memory by using the slice method. This lets us create views over existing memory directly as spanf instances, allowing us to perform operations like viewing the first 10 elements of a 100-element array without the need to copy elements to perform heap allocations of any kind. In all cases above, including the ones dealing with raw native pointers, spanf provides type-safe access to the memory while maintaining the performance of raw arrays. This provides enormous benefits to the authors of unsafe code today. Unsafe code is expensive to design and maintain due to the fragility and risk of raw pointers. Spanf can function in the same scenarios as native memory without the need to worry about buffer overruns or dangling pointers. There's also a variant of spanf called read-only spanf, which provides read-only access to contiguous areas of memory. This means it can hold any value which converts to a spanf, and additionally immutable types like system.string. This makes it the true universal receiver of contiguous memory in .NET. Now let's switch to Visual Studio and demonstrate what all can be done with spanf. For this demo, we're going to be demonstrating how spanf can help us avoid allocations in straightforward parsing situations. As I said earlier, I work on the C# compiler. We obviously do a lot of parsing, and our performance is very sensitive to the number of allocations that we do. So, as an example here, I've coded up a very simple method, is C# identifier. It takes a string and tells us, is this a valid C# identifier? Now, because it takes a string, that is kind of forcing a bit of a problem on anyone who's consuming it. Typically, when you're parsing, you're dealing with a large set of text, either in a string form, an array, or potentially a stream of values. Now, in order to basically look at the individual elements in these large pieces of text, I'm going to have to be allocating lots and lots of strings in order to do this validation. So let's start with a pretty small example. So this represents a very simple type declaration in C#. And if we want to get the first item in it, we're basically going to have to use the substring method on string. And my type is of length 6, so we'll grab that. And the second element starts at index 7. Now that we have the two values, we can call is C# identifier, passing them in. And if we run this program, we will see that indeed the program tells us true. The first one is a valid C# identifier, and the second one is not, because the identifier starts with a 1, which is illegal. Now, as we said before, this is really inefficient. This parsing routine, it isn't creating anything. It is simply looking at a region of memory and saying, does it match a very particular pattern? Yet, because I've chosen string as the parameter type, I am forcing all of my users to allocate a lot of unnecessary memory. And this extends even to other types. Like, let's say that we're parsing from a file using a stream reader. Typically there, we get our identifier back as a character array. Now, this means that I have allocated both an array for the characters, and now, in order to call is C# identifier, I'm going to have to create a new string entirely. So that's a whole new allocation over an array, really kind of eliminating any of the efficiency I would have got from being able to pool that character array buffer or reuse it across invocations. So let's take a look at where span can help us here. Instead of using a string, I can simply use a read-only span of characters. Now, notice how the implementation of the method still compiles. I had to make no changes to it, and yet everything is going to function exactly as it did before. Now, going back up here, we'll change our initial creation to use a read-only span of characters. So, in order to convert a string to a span, we just have to call the asReadOnlySpan method. Now, instead of substringing, I will just simply use the slice methods. And notice that this first block of code is compiling and running just fine. The slice method is returning another read-only span. So this is avoiding all of the allocations. It's just basically creating a very small view on my string, from which you can just simply read the set of characters and determine its length. Now, down here previously, where we had to basically create an array and then create a whole new string over it, once again, we can avoid this allocation entirely and simply pass the array directly. We don't even have to use the asReadOnlySpan method like we did for a raw string, because there's actually implicit conversions from arrays to both span and read-only span. So now, I have a parsing method. The contents of that parsing method are exactly what they were before. I didn't have to add any overloads for character arrays or int pointers or anything like that to maintain the efficiency. Instead, I was able to reuse the exact same code I had before. All I had to do was change the parameter type to a span instead of a string. And now my code is the same, my callers can execute me much more efficiently, and the code will run much faster. Usually developers can focus on the use cases of a type without having to understand the implementation. In the case of spanf, it is worth digging into the implementation a bit, because it provides the context into the performance characteristics of type, as well as several of the constraints. Now, the spanf type is actually a JIT intrinsic and doesn't have a direct C# representation. However, it can be approximated using the definition you see here. As you can see, the implementation contains two pieces of information: a pointer to the start of contiguous memory and the accessible length. The pointer is represented as having a type reft. This is not actually legal C#, as fields can't be of type ref, yet it's a good tool to help explain how the runtime represents this field and constrains its usage. The reft field acts much like a ref or out parameter, which has been around since the first version of C#. It specifies a location in memory which contains a value of type t. This memory can be on the heap, on the stack, or even native memory directly. The length field then specifies how many elements can be accessed from this location in a contiguous fashion. This layout allows for spanf to have the same performance characteristics as a normal T array. The location of an element can be calculated directly by applying the index to the data pointer, just as is done with arrays. There is no need to use an additional offset as done with array segment. Also, the use of a ref returning indexer means values returned will have the same performance and usability characteristics as you expect from an array. The returned elements can even be directly mutated and passed as ref parameters. The ref parameter analogy also extends to the limitations of spanf. Recall that it is legal for ref parameters to refer to locations within objects, fields, array elements, or even the evaluation stack. Such values are called interior pointers. These are very expensive for the GC to track and hence are not allowed in the heap, only the evaluation stack. This is why C# restricts you from capturing such values in lambda expressions, iterators, or async methods. Such a capture would necessarily push the value into the heap, which is not supported by the runtime. The same limitations apply to spanf, or any type which contains a spanf reference. Any such instance of a value logically contains a reft and hence cannot be in the heap. C# 7.2 has added a new feature to support this concept as a first-class item, called ref structs. All types which contain spanf fields must be labeled as a ref struct, and C# will then enforce the same restrictions on instances of those values as it does for ref parameters. It additionally prevents them from being used as a generic argument, box to object, or implementing any interfaces, all of which could lead to the value being moved into the heap. These limitations don't affect the main use cases for spanf. For example, parsing and data manipulation tend to be synchronous and compute bound, and hence are perfect for spanf. Yet many of the issues we talked about in the demo around unifying APIs to a single type apply to both synchronous and asynchronous operations. But spanf can't be a solution for asynchronous methods, as it requires the values to be stored in the heap. This is where memoryft comes into the picture. You will notice that memoryft looks a lot like arraysegmentft. It wraps a managed object, specifies an offset and a length bound for it. Because it's a typical struct and not a ref struct, it can be stored on the heap and used in asynchronous methods. This allows for operations like taking a slice of array as memoryft, passing it to an asynchronous method, and then converting it to a spanf when you actually need to do a synchronous computation. Like spanf, memoryft also has a read-only variant called read-only memoryft to represent memory which cannot be modified. This implementation produces read-only spanf values for processing. So far, we've only talked about arrays for memoryft, but it is also capable of wrapping other memory types, including object pools and native memory. This is done through the type ownMemoryft, an abstract class which allows for fine-grained control of memory lifetime. This video won't dive into this type, but it's a great item to follow up on if your code deals with tightly managed memory situations. All these features mean that memoryft and read-only memoryft can serve as our universal representation of contiguous memory in the heap. Now, let's switch to Visual Studio again and demonstrate how memoryft and spanf interact with each other. So now we're going to do a demo on how we can use memoryft in an asynchronous method in conjunction with a spanf synchronously operating on values. We're going to start with this sample we were using earlier of just parsing out C# identifiers from text. Now, let's imagine the scenario where we're not dealing with a fixed block of text. Instead, we're reading data from a file or the network. And in order to keep our application responsive, we're going to be using asynchronous operations to read. So the API we would define is a simple bool returning async method. So we're going to define a async task of bool. And this is going to take a memoryf_char, where we're going to be reading the values writing the values to, and a reader where we're getting the values from. Now, as we said before, the .NET APIs have been augmented to have support for the memory and span types. This means I can now use reader.readAsync to write directly into the memory value instead of a raw array like you would have done before. So we're going to capture the count of values that we read into this memory value. Now, once this operation is complete, the data read off the network is going to be going into this memory value, and it's going to have the length count. Now, there's a property on memory, as we showed before, called span, and that gives us a span over the memory as it exists in this point of time. So in order to get this identifier out of the memory, all I have to do is grab the span, slice it down to count values, and I have my C# identifier. So we'll just call it C#. Now we'll just pass this value to C# identifier. We will grab the span off of it and slice it down to this count method. And here, now it's all held together. We have an async API using memoryft, which is plugging directly into our synchronous method. And this is a great example of how you can combine synchronous and asynchronous APIs to give a nice uniform API for all of your consumers. In addition to the spanf and memoryt types being shipped in .NET Core 2.1, many of our existing types are being updated to accommodate their uses. APIs which previously took arrays, strings, array segments as arguments now contain overloads for span and memoryft. For example, parsing APIs on core types like int, float, and datetime can now be provided a read-only span of chars instead of forcing developers to allocate strings as they previously did. At the same time, we're providing the following guidance on new APIs. When dealing with contiguous memory, consider using the span and memoryft types. For synchronous methods, prefer span or read-only spanf if the operation is read-only. And for asynchronous methods, prefer memryft or read-only memryft if the operation is read-only. Finishing up, I want to rehash what we've talked about today. spanf and memryt allow us a universal representation of contiguous memory in the .NET ecosystem. APIs today, which have a variety of overloads for arrays, array segments, native memory, and strings, can now be simplified to a single implementation without sacrificing performance or type safety. Thanks for watching.